I'd like to start by paying tribute to my friend and co-author Ken Edwards, who passed away last year, as it happens on the 13th day of the 8th month. He became interested in tiling just under 20 years ago, and I'm pretty sure was the first proud owner in Thailand of the book by Art and Jenny. Ken came up with the idea of a fence tile, a tile made up of two pieces a fixed distance apart. And he first used these to generate Pascal-like triangles whose rows sum to give interesting sequences. And he then found a bijection between fence tilings and permutations. And the work I'm presenting today follows on from that and stems from his final communication with me about tiling. So we start by looking at the permanent of an n by n matrix. So if we talk about pi I as being the functions that give all the n factorial permutations of the numbers 1 to n, so this is an example, then the permanent of the matrix is given by this expression here, which is basically the same as the determinant but with all plus signs. And as the name might suggest, permanents are related to permutations, and we can specify certain types of restricted permutation by setting the elements of the matrix equal to 1 if I is allowed to move to j, and 0 otherwise. And then the number of possible permutations is the permanent of m. So the simplest example is if all of the elements of the matrix are 1, so all moves are allowed, and then the number of permutations, it's easy to see, is just n factorial. If we knock out the leading diagonal, put those to 0, then we get the number of derangements. So the permutations we're interested in today are ones where pi I minus I is a member of a set, a finite set D of elements, and if to enumerate those permutations, they're actually equal just to the permanent of a Toeplitz matrix, who's made of 1s and 0s, and the dth diagonal above the main diagonal is all 1s if D is in the member of the set big D. So to evaluate PND, there is actually a sort of a general procedure which effectively is doing a Laplace expansion of the permanent, but in some cases, some simpler cases, it can be done another way. And for example, if pi minus I is equal to minus 1, 0, 1, then it turns out that the PND is given by the Fibonacci numbers. So the way to show that is by using a bijection. So it turns out that this is where the fence tilings come in. So there's a bijection between the fence tilings of an n board and the permutations of the numbers 1 to n, which satisfy this condition here. So what we do is, well, first I need to say what a fence is. So a fence is a tile made of two pieces, half by 1 posts, separated by a gap of width d. D could be 0, but otherwise it's a non-negative integer. And the rule is the following, that if D is not negative, then we have to place our fence. An example of the fence with this property is F0 or F1. We have to place the left-hand side of the fence in the left-hand side of a cell. Otherwise, if D is less than 0, then this corresponds to a fence with a gap of minus D minus 1, and which we denote with a bar over the F. And that has to have its left post placed on the right-hand side of the cell. So an example is the yellow thing here. So that's actually a fence with a 0 width gap, which must be placed with the left-hand side of the fence, the left post, in the right-hand side of a cell. Okay, so the bijection you can see in this example here of a permutation 1, 2, 3, 4 going to 1, 3, 2, 4. The points which don't move 1 and 4 corresponds to F0 tiles, and 2 going to 3 corresponds to this tile here, F1. So we look at the 2 here and then see where the other half of the fence is, and it's in the 3rd cell. And similarly, the 3 going to 2 corresponds to this yellow fence. We look at the left-hand side, we look at the left-hand side of the cell and see what fence is there, and the other side of the fence is where it goes to. So tiling an M board with these types of tiles corresponds to a permutation obeying pi r minus I equals -1, 0, 1. Now F1, you always have to fill an F1 with an F0 bar, and that this combination here is effectively a domino. So we're basically just tiling with squares and dominoes, which means that the number of permutations is just the Fibonacci number Fn. So those groupings that we just saw, effectively domino and square, are examples of metatiles. And a metatile is a minimal grouping of tiles that takes up an integer number of cells and leaves no gaps. Now in the case we just saw, it's very simple to work out what the metatiles are. And I should say all tilings can be expressed in terms of metatiles. They're the fundamental object. But when we start to tile with other fences, and large number of them, things start to get complicated in the way of what possible metatiles there are. And a systematic way to generate them is using a directed graph, or digraph, an example of which is this. And the 0 node here corresponds to the empty board or a completed metatile. And then each other node represents the rest of the board once we've put some tiles on it, starting at the next gap. So for example, if I were to put an F3, that's a fence with a gap of 3, which is 6 half cells, I'll end up with 6 half cells plus the other end of the fence, the other post of the fence. And the bar just means that I'm starting on the right hand side. The gap starts on the right hand side of a cell. Each arc represents tile or tiles, and we can get a metatile just by starting at the 0 node and just making some sort of walk back to the 0 node. So lots of possibilities you can see for generating a metatile. So it turns out that once we've drawn the digraph, it's actually, there's a formula which in some cases will, or for some digraphs, will actually give us the total number of tilings, or at least a recursion relation for the total number of tilings. So to understand that formula, we need a few definitions. So an inner cycle is any cycle which doesn't include the 0 node, such as this one here. A common node, if you have more than one inner cycle, if you have a common node, is simply a node which is common to all of the inner cycles. So here we have 2 inner cycles, and actually in this case either this one or this one we could call a common node. A common circuit includes the 0 node and common node once each. So an example would be along here and then back to here. An outer cycle is a cycle which doesn't include the common node. So an example would be this one here. And an outer metatile, each of these paths which go from 0 back to 0 correspond to a metatile. So this one here we call an outer metatile. And the length, which is important, we want to know how long these metatiles are, is actually simply the number of tiles, because each tile is composed of pieces of length half, 2 pieces of length half. So the main theorem we're going to use here is a rather compact result, considering how complicated things can get, and it simply it gives us the number of tilings, the recursion relation for the number of tilings. The quantities involved are just the lengths of the various things, so lengths of the cycles, LR, lengths of the outer cycles, lengths of the common circuits and so on. It's somewhat surprising that this formula is so compact, given that some very complicated things can happen. I mean, to form a metatile, you could go to here and then execute this cycle a number of times, and then this one, and then go back to this one, and then you return here to end your metatile. So in spite of that, the formula is relatively simple. So the main result we're presenting today stems from that formula, and it gives you an identity concerning the number of permutations, which is the same as the number of tilings. And we're defining generalized Fibonacci numbers as a sequence where the coefficients in the recursion relation are all positive integers. Okay, so where does this theorem come from? Well, basically, we start off with Gn, the generalized Fibonacci numbers, is simply the number of tilings which lack outer metatiles. And to get this, we start off with our main result concerning tilings, and we just say, well, what happens if we don't have any outer metatiles? Well, that corresponds just to knocking out this cycle here. We just ignore this cycle here and then count. So to do that, we just ignore this sum here, which involves the outer cycles, and that just leaves us with these three terms here. And these, you can see, all have well, coefficients of +1. So we can call those, we're going to call those generalized Fibonacci numbers. Okay, so to get the rest of our main theorem, we use a combinatorial argument or tiling argument and ask how many tilings of an n board use fences corresponding to the elements of D, our allowed displacements. So by the bijection, the first answer 1, is just PND. The second answer, what we do is we condition on the final outer metatile. So the first possibility is that the complete tiling contains no metatiles, and we already worked out that the number of such tilings is Gn. So that's this possibility here. Otherwise, if it does contain an outer metatile, then we condition on the position of the final outer metatile. And the number of ways to tile then is the number of ways to tile before the final metatile times the number of ways to tile after the final metatile, and we end up with this, and then we just sum over all possible k starting positions and all possible outer metatiles, and then equate the two answers. So now we finally actually, the example I've been showing all the time, we now finally turn to that example and actually work it out in detail. So guessing this identity is basically down to drawing the digraph and working out the lengths of the various things. So in this particular case, we have two inner cycles, f bar 0 followed by f1 bar f3, which is of length, you've got 3 tiles, so it's length 3, and we've also got this one where we start with this loop here and go back down here, which is length 5. Common circuits with this one, f3 f0 bar to here, and then we can either go this way and back, which gives us an extra 2 tiles, making a length of 4, or we can go this way and back, which will give us an extra 4 tiles and a length of 6. And there's just one outer cycle, which is this one from here round to here, which has 5 metatiles in total. So plugging these numbers in gives us, from our main theorem, this result here, where our generalized Fibonacci sequence is this G. The 3, 4, 5, 6 come from these numbers here, 3, 4, 5, 6, and the outer cycle length 5 appears in these 5s here. The number of permutations with that restriction -2, -1, 3 from our sort of original big formula turns out to be this, which is this sequence in the online encyclopedia. Our next example, this one, for some d, you actually end up with rather simple looking numbers of permutations. In this case, this is actually the number of Fibonacci numbers, the Fibonacci numbers squared. Now, in this case, we have two possible common nodes. If we choose this one to be the common node, there's only one outer cycle. If we choose this one to be the common node, then we actually also have an additional two outer cycles here. So we end up with two possible formulae from this digraph. Because things are zero apart from when Pn is n is 0 modulo 3, things actually simplify a bit, and we end up with these relations for the Fibonacci squares. In the first case, relating them to something a bit like the Pell numbers, and the second case relating them to sort of something like the Fibonacci numbers. So these are some key references, and I'll finish it there. Thank you very much.